This conference was prepared jointly with the Safra Center, so I decided to spend 2 minutes telling you about the Safra Center for Bioinformatics at Tel Aviv University. The center is now in its 16th year. It encompasses nearly 50 research groups all around campus. A lot of activities, more than 50 fellowships per year. Perhaps the number I'm proudest of is 22 alumni by now in academic positions and over 100 in the industry. A few years ago, Microsoft ranked organizations in bioinformatics, and Tel Aviv ranked 11th in the world and the first university outside USA. So our current mission meets very well with the agenda of this workshop. We want to bring bioinformatics closer to the clinics, and this means to create research partnership with the industry. Sorry. It has life of its own. And we are setting up a health data science hub at the university. We want to expand education, especially to clinicians in the computational part. Okay, so one slide that fits everything in this conference. We want to change the future medicine from one size fits all to personalized or precision by tailoring the treatment to the particulars and the data of the patient, and this requires computation. So I'll tell you about 2 stories. The first was led by Dan Koster, a graduate student in the group, who is also an MD student. And we are dealing with breast cancer, which is a highly prevalent breast cancer, the most prevalent one in women. And to try to get ready for and identify early the cases of women with breast cancer, there are certain screening tests done either by mammography or by breast exam that are followed, if needed, by deeper tests and biopsies. And this is expensive and difficult to manage, and we thought maybe there is a better way to do this by using EMRs. So the data that we used was based on periodic checkups, בדיקות תקופתיות, done at Ichilov, where people come over time, once every couple of years, and take tests. The tests are very extensive. Some 600 parameters are measured. And the cohort for women was more than 6,000 females and nearly 12,000 visits. And we matched this data with the cancer registry, Rasham HaSartan, and we found 77 women who developed breast cancer later, within 2 years from the last visit. So we looked at the data and we compared the data for the breast cancer, the positives, to the negatives. Not surprisingly, there was a very strong significance to age, for example. So to compensate for that, we generated a sub-cohort which is matched to the cancer cohort, and it was smaller but still substantial, and you see here that no significant differential feature exists within this matched cohort. So one technical slide, the data that we have, if we look at it over time with a scale of age, each subject comes for multiple visits at different ages. So the data is left truncated, and at some point either the study finished, so we don't have additional data, so it's censored, or the subject was diagnosed for cancer. So these are the positive cases. And we want to compute the survival function by summarizing the fraction of patients that are healthy at every time point. So we do this by scanning over the time points and counting the number of patients at risk and failure event at each time. And we can plot this fraction of patients at risk as the survival function, which will be the main tool that we'll be using, or the Kaplan-Meier curve. The one difficulty in our setting is that we have multiple measurements per patient, so the solution for this is to create what so-called pseudo-objects, breaking each the intervals into individual visits. And we also chose to move everything to the start, to the date of the first visit. So all the now age is one of the model parameters and not the x-axis of the curve. Once we have this set up, we create a survival tree by splitting the patient, the way it's done in a decision tree, finding the best value of the best feature that splits the data, and the splitting criterion is the survival distributions of the two subpopulations, on the left and on the right. And we use the log rank test to obtain a p-value. And the lowest p-value is the splitting criteria, and we do this recursively until the best split is not significant. And actually, we don't do this for one tree, but we do it for an ensemble of trees in the random forest fashion. So we subsample the features at every tree, at every node, and we generate 500 trees. And we obtain a weighted average. Given a new sample, we propagate it through each of these 500 trees, and we take the average of the 500 Kaplan-Meier curves that we obtained. So this is the technical tool, and here are the results. On the left, you see the results for breast cancer, area under the precision recall curve, and our approach appears in blue, and you see several other common classifiers. I should note that the standard Gale method, it's measured in area under the ROC curve and not the AUPR, but we still do better than this criterion for the first year and a half. So the x-axis here is the time from the last test to the diagnosis. So you see that we can predict better than alternative methods up to 2 years in advance. We repeated the same analysis for data for prostate cancer. We took the males in the same cohort. We had some 11,000 males, and 56 were diagnosed with prostate cancer within 2 years. And you see here that our approach does better than the alternative methods. In fact, for the first 6 or 9 months, it's even significantly different when we do repeated sampling of the data. So to summarize this part, we can obtain better personalized predictions by using results of standard tests of healthy individuals. Unlike the screening tests that exist today, the screening tests today are aimed to identify women or men who already have the disease. We aim to do this to predict development of disease later, even if the person is completely healthy today. And I didn't show it, but we also had data on mammography and clinical breast exam to a part of the cohort. And we saw that some cases where women developed breast cancer later had very high scores according to our criterion, but tested negative in both CBE and mammography. So it could be used as a complementary approach to existing screening practices. And we are currently planning a broader validation of this approach, and perhaps with the larger cohorts, we will be able to expand it to additional types of cancer because the method is generic. Let me now switch gear and talk about another project led by Nimrod Rapaport, a PhD student in my group. And here we are talking about integration of multiple data types. So the Cancer Genome Atlas is a fantastic resource that has been developed for over a decade now. It contains data for more than 10,000 individuals with cancers across some 30 cancer types. And the data is extremely diverse. We have a mutation, copy number, gene expression, methylation, microRNA, protein measurements, and clinical data. So it's really a fantastic resource. However, the data, the omics data is extremely diverse in terms of distributions and in terms of the number of features and their properties. And on top of this, the clinical parameters are some numerical and some categorical. So the question is, can we use multiple data types together in order to obtain better subtype identification in cancer? So there have been highly successful stories of using a single cancer type and applying clustering to identify subtypes. But the question that we set out to ask is, can we do better by looking at multiple omics together? So we looked at the literature, and actually there's quite a lot that was already done. Multiple approaches. I won't get here into the details. And there are quite a few algorithms that were implemented and were available for testing. Some of them were developed in the machine learning literature. They fall under the name of multi-view methods, and they were not even, some of them were not even tested on biological data before. So we wanted to benchmark these algorithms. And we took 10 data sets from TCGA, a few hundred patients per data set. And the omics that we used were gene expression, DNA methylation, and microRNA. And we put aside the clinical information in order to use it for validation of our results. So how did we assess the benchmark? Each of these algorithms produces a clustering, a partition of the patients. And we have the information about the survival of these patients. So we can plot a survival function for each cluster. And again, use the log-rank test in order to see how separate they are. And we can also use the clinical labels that were available for this data. Before I show you the result, during this process, we also came up with our own algorithm, which we call NEMO, very simple algorithm. So it looks at each omic separately and computes sample similarities based on a Gaussian kernel using the k-nearest neighbor per omics, and then average the similarities across the omics in the most straightforward way. And now we have a graph where the nodes are the patients and the weights are, the edge weights are the similarities, and we perform spectral clustering. So actually using the graph Laplacian in order to do the clustering. And unlike the standard way of choosing the number of cluster, we decided to look at the difference between the eigenvalues, consecutive eigenvalues, and multiply it by the number of the eigenvalues, because we observed that nudging the number of clusters slightly higher helps the results. And note that this approach of averaging the omics can directly address missing data without need for imputation. So here are the results of the 9 algorithms across the 10 data sets. And here you see the number of data sets that had significant result in terms of survival. You see that NEMO did best. In terms of clinical enrichment, we tied for the best, and we were the second fastest. Here is a similar analysis looking at the average significance over the 10 data sets. And in a particular test in leukemia, we also obtained a better result than all the alternatives. So in summary, we created an extensive benchmark, and we developed our own algorithms and show that we can improve the results. The improvement is not always. There are some cases where that it's better to use independent omics. And it's an interesting question, what is the right approach here? The software is available from our group, and I would like to thank you and thank my group for all this study.
Thank you. Thank you, Ron. Thank you, Ron. We have time for one very short question.
Hi, thank you. For the first part of your talk, I was wondering, this kind of medical data analysis, we sometimes rediscover something that physicians already knew in a more quantitative way, and sometimes we discover a new mechanism. So I'm just curious, what was it this time? And did you do some ranking of the variables?
Yeah, I didn't show it, but we did some ranking of the features, and some of the top features made sense, I can say, but they were not, completely obvious to the oncologists that we talked with.
Thank you.